Now we're going to go over our Lewis structures. So we start out by looking at a couple of pairs of elements, and we want to know if they form ionic and covalent bonds. In both cases we have sulfur. Sulfur we know is a nonmetal. And normally the easiest way to determine whether we have ionic or covalent bonds is whether we're dealing with two nonmetals or a metal and a nonmetal. The first pair, sodium and sulfur, is a metal and a nonmetal, so that will usually be ionic. And sulfur and hydrogen are two nonmetals, which gives us covalent. Now, the rest is looking at covalent bonds. So how many electrons do we get by forming a covalent bond? The atom gets one. Recall that a single bond is one electron from each atom for a total of 2 electrons. So each atom gains 1 electron from a single bond. Double bond is 4 electrons that are shared, so it gains 2, and it gains 3 electrons in a triple bond. Now, there's a lot of general rules that we can start to find in terms of numbers of bonds. So hydrogen has 1 electron. It needs 1 more electron to get to the configuration of helium, so it needs 1 bond. Carbon has 4 valence electrons, therefore it needs 4 more electrons, which it would get by forming 4 bonds. Nitrogen starts with 5 and needs 3 more. And oxygen starts with 6 and needs 2 more bonds. All right, draw a Lewis structure for HF. We have 2 electrons in bonding pairs. We have 3 lone pairs on fluorine, times 2 electrons is 6. There's 8 electrons around fluorine, 2 around hydrogen, and yes, everyone has an octet. Remember again that for hydrogen, an octet is 2 electrons, not 8. We're going to do the same thing with hydrogen and sulfur. There's our Lewis structure for hydrogen and sulfur. We need 2 hydrogens and 1 sulfur. There's 4 electrons in bonding pairs. Sulfur has 2 lone pairs, or 4 electrons. Sulfur has 8 electrons. There's 2 electrons around each hydrogen, and everyone has an octet. All right, what about boron and hydrogen? This one's a little bit more complicated. If we find boron on the periodic table, we find it in group 13, which means boron has 3 valence electrons. That means it can form 3 single bonds. So it can bond to 3 hydrogens and make BH3. And there's no electrons left over to put as lone pairs around boron. So does each element have an octet? The answer is no, because boron only has 6 electrons. Now, have we done something wrong here? We haven't, because each hydrogen only has 1 valence electron. So we only have 6 total valence electrons. Remember that group 13, the column containing boron, aluminum, gallium, indium, and thallium are exceptions to the octet rule. And in general, those atoms often only have 6 total electrons. Turns out, and if any of you are going to take organic chemistry in the future, you may learn something about this. The fact that boron only has 6 electrons ends up leading to some very, very interesting reactivity. Here now we're just drawing Lewis structures. Now while I do these, I will make sure to put in all of the lone pairs. But as we move on through time, that's something that will sometimes get left out. In nitrogen, N2, there is no true central atom because both atoms are the same. Part C, we have formaldehyde. So let's go step by step through this one. Carbon has 4 valence electrons, plus 6 for oxygen, plus 1 for each of the hydrogens is 12 electrons. So we're going to put carbon in the middle because it needs the most bonds. And we can draw single bonds to each of the other atoms. So we've used 6 electrons, we have 6 left over. So we can put those 6 on oxygen. We've used the remaining 6, and all of them are gone. The problem is that while hydrogen and oxygen both have octets, carbon does not. And so in order for carbon to have an octet, we're going to have to take not the oxygen away, but we're going to take that lone pair away. Where's that lone pair going to go? It's going to go as a double bond. And so now oxygen still has an octet, but carbon does as well, and everyone is happy. Part D is ammonia. This is actually very, very similar to the NF3 example we did already. 3 single bonds to nitrogen with a lone pair on nitrogen. Chloroform, CHCl3 gets carbon in the middle, single bonded to each of the chlorines, as well as the hydrogen. Now this is probably a good example of why we don't always draw the lone pairs in. For now, you should be doing that. And you also want to be very careful when you're doing some of the homework questions. Some of the homework questions will specifically say on them, make sure all of the lone pairs are drawn in. So don't forget to do those. But we don't necessarily have to, so we could leave it like this, or we can put them all in. And finally, our last one in this group, SO2. We're going to do this one completely. So both sulfur and oxygen are in the same column. Both have 6 electrons. So we have 18 electrons total. So we can start by doing that. That uses 4 electrons and leaves us with 14. And if we put 3 lone pairs on each oxygen, now we've got 2 electrons left. And we'll put those on sulfur. And so we've used all of our electrons. There's just one problem right now. And that's, of course, that sulfur doesn't have an octet. So what do we do at this point? Well, as we've done before, we'll take away a lone pair and make a double bond. The problem is what we find next. So at the end of the lecture on Lewis structures, I talked about formal charge. And let's calculate the formal charge on these atoms. So sulfur here should have 6 electrons. It has 2 electrons in a lone pair and 6 electrons in bonds. So that says this sulfur has a charge of +1. The oxygen, on the other hand, should have 6. It has 6 in lone pairs and 2 in a bond. And so we get a charge of -1. Now, in theory, if you left off at this point and gave that as an answer, that would be okay. However, we always want to reduce charges as much as we can within a molecule. And the way that we can do that here is by taking another lone pair on oxygen and making it into a double bond as well. Giving us that. Now, if you go through and recalculate the formal charge for the sulfur in both oxygens, you'll find that now both of them are 0. But maybe another problem has occurred to you. And that's the fact that this sulfur sorry about that. This sulfur has 10 electrons around it. 4 from this double bond, 4 from this double bond, and 2 from the lone pair. Now, is that a problem? Well, if we were dealing with carbon or oxygen, having 10 electrons is a problem. But because sulfur is in the 3rd row of the periodic table, we can and often will have more than 8 electrons around some of those elements. Very, very common for sulfur as well as phosphorus. So that's okay. And it turns out that this, and I'll redraw it over here so you can see it better. Because it doesn't have any charges, is a better structure than the first one. Neither is wrong, but again, this is a better answer. Right, finally in part 8, we have some nomenclature. Now the first thing you need to do is go through in these cases and determine how many of each atom you need. So for carbon and chlorine, CCl4, which makes it carbon tetrachloride. Nitrogen, as we know, requires 3 bonds. So this is nitrogen tribromide. And the remaining ones, it's just a matter of doing them from the formulas. Now remember, for nonmetals, if the first element has a number given, then we need numerical prefixes for both. So dinitrogen, pentasulfide, tetraphosphorus. There's 10 oxygen, so we use the prefix deca, so tetraphosphorus decaoxide. Here the first element is bromine, and there's only one of them, so we don't need the prefix. Also, just as a note, and this is a very common error, compound names, element names are not proper nouns, so they should never be capitalized. So make sure you know these prefixes. The one I especially emphasize, though, is this one, tetra. Over the years, I've seen many different wrong answers for 4. Things such as quad, tert, buta, and several others. But the only prefix for 4 is tetra.